Thermodynamics, Chapter 3, Lecture 5. So this is the last lecture of the chapter. We'll talk about the ideal gas law and the other gas laws. So first, let's talk about the ideal gas law equation of state. So first, what is an equation of state? Equation of state is any equation that relates to pressure, temperature, and specific volume of a substance. The simplest and best known equation of state for substances in the gas phase is what's known as the ideal gas equation of state. This equation predicts the pressure, volume, and temperature behavior of a gas quite accurately within some properly selected region. So there's different forms of the ideal gas law equation. PV equals RT. R is known as the gas constant. It's the universal gas constant, RU, divided by the molar mass. So some of these you can calculate. RU is given by different values depending on the units you use. Our front of our book or the back of our book has a table that you can find these in. So for some constant, for some different substances, air, for example, has an R of 0.2870, helium, argon, nitrogen. All these are constants that you can look up. Of course, the ideal gas law has many expressions depending on what units you use. One equation I like to use is the one above. PV over T equals a constant. So if you know, this lets you calculate a lot of different things. For example, if you know everything but one thing, you can obviously use this equation to calculate it. But if you hold temperature constant, for example, you just cross out temperature on both sides of the equation and get PV equals a constant. Or if you hold, if the pressure is the same, you can cross off P1 and P2, and you'd have V over T equals a constant. So this is kind of very useful. So is water vapor an ideal gas? Well, at pressures below 10 kilopascals, you can treat water as an ideal gas. However, higher pressures, this becomes unacceptable, particularly in the vicinity of the critical point of the saturated vapor line. So what does this mean for us? It means that in air conditioning applications, the water vapor in the air can be treated as an ideal gas because we're in the kind of Goldilocks region for that, up in here. In steam power plants, however, we cannot do that because we're down here in the region where there's just too much air involved. The ideal gas equation is very convenient to use. However, gases deviate from ideal gas behavior significantly at states near the saturation region and the critical point. This deviation can be accurately accounted for by the introduction of a correction factor called the compressibility factor, Z. The compressibility factor, Z, is defined as follows. PV equals Z RT. So this is just the ideal gas law, except we put the term Z in here. So we can solve for Z is equal to PV over RT. We can also define Z as the V actual over the V ideal, the volume actual over the volume ideal. The compressibility factor is unity for ideal gases, obviously, and it's bigger than 1, equal to 1, and less than 1, depending on the particular gas and the temperature and pressure. So although gases behave differently at any given temperature and pressure, they behave very much the same at temperatures and pressures normalized with respect to their critical temperatures and pressures. This normalization is done as follows. We define what's called the reduced pressure to be the pressure over the critical pressure, the reduced temperature to be the temperature over the critical temperature, and the reduced volume to be the actual volume over the RT critical divided by P critical. So here's a chart of the Z factor. So, what you need to do is you come in at the reduced pressure, then you find the corresponding reduced temperature you're at, then you run over and you determine the Z value. The further away Z is from unity, the more the gas deviates from ideal gas behavior. The following observations can be made from the generalized compressibility chart. At very low pressures, gases behave as ideal gas regardless of the temperature. At very high temperatures, ideal gas behavior can be assumed with good accuracy regardless of the pressure, except in the case when the reduced pressure is much, much bigger than 1. The deviation of a gas from ideal gas behavior is greatest in the vicinity of the critical point. So here is two kind of graphics to illustrate most of this. So A real gas, as pressure goes to zero, it becomes an ideal gas. And as long as we stay away from the critical point, if and stay in these regions as illustrated here, very high temperatures, very low temperatures, but the specific volume is very high. The gases pretty much behave as ideal gases. So in general, if we're dealing with air conditioning systems, we treat the air as an ideal gas. However, if we're dealing with steam systems, we can't treat water vapor as an ideal gas because we fall beneath this region here. So let's take a look at how to use the generalized charts from example 311. Determine the specific volume of refrigerant 134A at 1 million pascals and 50 degrees C using part A, the ideal gas equation state, part B, the generalized compressibility chart. Compare the values obtained to the actual value 0.021796 cubic meters per kilogram and determine the error involved in each case. So first thing we can do is we can look in table A1 and we can find the values that we need for to determine the Z factor. So looking in the chart, and I've clipped table 1, and it's a pretty long chart, but here at the bottom you can find R134A. So you can find the gas constant, you can find the critical temperature, the critical pressure, and the critical volume. So the specific volume of refrigerant 134A under ideal gas law assumption is just RT over P. So we can plug those values in and we can calculate what the specific volume is, 0.026325 cubic meters per kilogram. Therefore, if you treat the refrigerant 134 as an ideal gas, you get an error of about 20%. So let's look at how to do it with the compressibility factor. So here we have to calculate, first we have to calculate the reduced pressure and the reduced temperature. Plugging in the values for the pressure and the reduced pressure, we get 0.246 for the reduced pressure, 0.863 for the reduced temperature. So we can look back in the compressibility chart and determine Z is about 0.84. Now this chart is very hard to read, and so would I get it exactly 0.84 from the chart? Probably not. I might get 0.8 or 0.75 or something like that, but it's just it's a rough approximation. So using their value of 0.84, V is equal to Z times the ideal V, which we calculated from above, you get a specific volume of 0.022113 cubic meters per kilogram. So if you compute the error, it's about 2% error from the known value. So here you can see how using the compressibility chart can greatly improve your accuracy. So let's take a look at example 312. Determine the pressure of water vapor at 600 degrees Fahrenheit and 0.51431 cubic feet per pound mass using steam tables, the ideal gas equation, and the generalized compressibility chart. So first thing we need to do is go to table A1E and look up the values for the water. So here I've included a clip of table A1E so you can kind of come across and you can read the R value, you can read the critical pressures and the critical temperatures. So let's do part A using the steam tables. So here we can look in table A6E. We can come to, we have to sort of do it kind of backwards. I mean, and I've clipped a part of this. So what we're given is the specific volume and we're given the temperature. So we have to look down through the specific volume chart and try to find the value that's closest to the specific volume that we have. And fortunately, we found one that's exactly equal. It turns out it's in the pressure of 1,000 psi. Notice this is also the TSAT. So that kind of verifies that we're superheated, right? Since we're at 600 degrees Fahrenheit and at this pressure, the saturation temperature is 544.65 degrees Fahrenheit. So we find our value for V. We can sort of in the chart, and so we can determine that we're at a pressure of 1,000 psi. So these are experimental values, and so this is very accurate here. So for part B, we can use the ideal gas equation to calculate the pressure. So P equals RT over V. R is given. T we have to convert to Rankine, remember. V is given. So we can calculate what the pressure is. It's 1,228 psia. So if you compute the error, it's about 23%, which is significantly large. Let's use part C to determine the correction factor from the compressibility chart. First, we have to calculate the reduced volume and reduced temperature. So these are the equations to calculate that. Then you can look at the compressibility chart. This is chart A15. And notice here that even though these are in English units, we're going to the A charts. There is no A15E. Now, this is a very confusing chart because it has, on the y-axis is the Z value, on the x-axis is the reduced pressure. It's also got the temperatures, the reduced temperatures kind of curving down, like curves that go from 1 and kind of curve downward. And it also has the reduced volumes that go this way, kind of from high to low. So how do you read this thing? So it's a difficult chart, and I've shrunk it down a little bit, but even so, it's still difficult to read. So first thing you want to come to is the reduced volume, 2.372. So you can see the values here. Here's a VR equals 0.7. So you kind of come up to these values here. Those are the reduced volumes. So you get about 2.3. So right here's about 2.4. So we follow this down until we run into the reduced temperature of 0.91, which is about it right in there, right? And then we come all the way down, and we can read off what the reduced pressure is. It's about it's about these are 10 10 increments here. So this is about 0.32 is what I would say. He has a value of 0.33. That I'm sure that's determined from a computer. That's not determined from this chart because you can't read that exact value off the chart. But we'll go with his value of 0.33. So once we have that value, we can just multiply by the critical pressure, and we can get the pressure 1,056. So if you compute the error, it's about 6% error. So that's most generally acceptable for most engineering practices. You can do better with a better chart, of course, and of course software is the best way to determine these Z factors.